Okay, this is a quick video about interference and diffraction, which are really the same thing. And specifically, we're going to cover these three cases, and we're going to do them in that order because that is the logical way to do it. So just so we make sure we're all on the same page, this is a double slit. You've got 1, 2 slits. This is the one that most people see first. And what do? You shine light at the double slit. Some of it goes through this slit. Some of it goes through this slit. There's a region where they overlap and then regions where they don't overlap. And then over here, there's really nothing at all. So naively, you would expect, okay, well, where they overlap, there's lots of light, so it should be bright. And where they don't overlap, there's less light. But of course, you're already at this video, so you know that's not what you see at all. What happens is you see bright and dark bands. In other words, it's very bright in some places and very dark in other places. And how do we explain that? Well, we explain it because light is a wave, of course. These are two waves. They start in different places. The bottom one goes a distance x1, the top one goes a distance x2. And even though they start out in the same part of the cycle, they end up at the screen at a different part in their cycle based on the difference in distances they go. What does that mean? Well, when you have two waves, if they line up perfectly, that's called constructive interference. And if they are anti-lined up, in other words, if the minimum corresponds to the maximum here, that's destructive interference. How do these waves combine? Well, superposition. You just add them point by point. Constructively, you end up with something really big. Destructively, you end up with nothing at all. And so you end up with bright spots and dark spots. Now, at any given point on the screen, you might see this, or you might see this, or you might see something in between those two. They don't have to be perfectly lined up or perfectly anti-lined, and that's why it starts from minimum, it goes up smoothly to maximum, and then it starts coming back down again. So you see all kinds of interference here. Okay, let's get this cleaned up so we can actually do some math. Here are our two light waves. Each of these waves is an electric field. Each of the electric fields has an amplitude, and it has some location it's gone to, and it varies over time. Notice I have A1 and A2 here because, look, we know that light decreases in amplitude the farther you get away. What we are going to do in this video is a couple of things. Number one, instead of talking about X2, I'm just going to say, look, this is X2 is really X1 plus some other amount, some phase shift. Okay, and the other thing I'm going to do is I'm going to do what's called Fraunhofer diffraction, which means I'm going to make my life much easier by making a couple of simplifying assumptions. Number one, I'm going to assume that the amplitudes are the same, even though they go different distances. The other thing I'm going to do is I'm going to say, look, I'm so far away from the slits that these two are essentially parallel. You might say, they don't look very parallel to me. Okay, I agree. In this picture, they don't look very parallel. The alternative is to do something called Fresnel diffraction, and it's much harder. So we're going to walk before we can run, and we're going to say, look, I know they're not exactly parallel, but they're parallel enough. What does that buy me? What that buys me is if I want to figure out the path difference between the two, all I have to do is drop a perpendicular from one of the lines to the other lines. So just to convince you that that's something that makes sense, let's say that I have two parallel lines, and I want to know how much longer one is than the other. Well, I drop a perpendicular, and then that's my difference. Okay, so I do have to do a little bit of geometry here. So if I do a little bit of geometry, I end up with something that says, okay, well, this distance delta, let's see, if this is theta and this angle is theta, then this is 90 minus theta, and so that angle is 90 minus theta. You get the idea. You end up with delta looking something like d sine theta. And what have I said here? Here I've said that the percentage of a wavelength that I change by, so that's a distance, is equal to the percentage of angle or phase that I change by. In other words, the argument of the sine changes by the same percentage that the wave distance changes by. So that's what's going on there. Okay, so what am I going to do with all this? Well, what I'm going to do with this is I'm going to park my phase angle up top, and then now what I can do is I can add the two waves together. So how do we figure out what happens at the screen? We simply add them together. So what does that look like? Well, we've got two electric fields. We add them together. And now the question is, how do you add two sine functions that don't look alike? Well, there are two ways to do it, and I'll show you both ways. Here's way one, which you're probably more comfortable with. Way one is you use trig identity. Sine A plus sine B is this thing, and if I plug and chug, eventually I'll end up with something that looks like this. And now here's a key thing. I actually don't care about the value of the electric field. What I actually care about is something called intensity, which is the average value of the square of the electric field. Why is that? Just think about this for a minute. We're talking about light. Light has a frequency of like 10 to the 15. That is so fast. We're humans are slow creatures. We can't keep up with that. So what humans actually see is an average value. Now, how do you find the average value? Well, the average value of this is just this. It doesn't change. The average value over time of this is super easy, because if you square sine and you take the average value, you just end up with a factor of 1/2. So you get a factor of 1/2 from here. That kills this too, and then it just goes away. All you're left with is some reference intensity times the cosine squared of phi over 2. So that's way 1. Now I want to use way 2. Way 2 uses complex variables. What does that mean? That means that instead of adding sine functions, I'm going to add exponentials. And the idea is, if I add 2 different exponentials, I'll have 2 different signs attached to my imaginary term, so that when I'm done adding the exponentials, I can just look at what the imaginary term is, and that'll tell me my signs. I know you're probably skeptical if you've never done this before, but I'll show you. We're going to get the same result. Okay, so if I add 2 exponentials, that doesn't seem at first to really make my life any better. It actually makes it seem worse. But look, I can do a little factoring, and if I do a little factoring here, and then I do a little bit more factoring. So what did I do? I pulled an e to the I phi over 2 out, and I end up with something that looks like this. Well, if you look at this formula and you compare to this formula, what you find is that what I've gotten written there is just cosine of phi over 2. Holy smokes. Think about this. I used the fact that I can factor out exponentials. So that's really why I wanted to go to complex land. Not because I like imaginary numbers, but because I like exponentials. I'm able to factor things out. And once I can factor them out, well, then I get my cosine of phi back. And then look, this is the same as this. And so when I look at a time average again, this piece will disappear. This piece will disappear, and I'll end up with this again. So I know you're probably not convinced at this point. You're probably like, I don't know, that looks pretty fancy, and what's the point? Okay, well, this is gonna pay off very shortly. Very shortly. Okay, so here we are. We have 2 slits. Okay, and just let's just get a sense of what this looks like. So if I were to plot this, right, then I get something that looks like cosine squared of phi, meaning depending upon where I look on this screen, depending upon where the phase angle is, I'll see something that looks like this. So at least that makes sense. That's consistent with what we've seen so far. Okay, so what do we do with this? Well, we can say that the maxes and mins, this is normally the thing books do first. They don't get the intensity till later. Look, we've already gotten the intensity. But look, we can say that when this condition is true, we'll get maximums. That's because cosine will be 1. And when this condition is true, we'll get minimums. That's because the cosine squared will be 0. You can play with the algebra and convince yourself that that's true. Okay, what's next? Well, what's next is, what if we wanted to do 4 slits? Okay, well, it's the same technique. We don't have to do anything differently, right? Now I just have to add 4 wave functions. And instead of saying x1, x2, x3, I'm just going to keep adding phi, 2 phi, 3 phi. And if you're saying, wait a minute, how do you know the phase is the same? Remember, I'm pretending that they're all parallel. So I just drop 1 perpendicular, or 2 perpendiculars, or 3 perpendiculars. The phase is the same for all of them. Okay, so if we were to do this doing way 1, oof. I mean, we could do trig identity over and over again. That sounds pretty awful, actually. And another thing is, even if you could do it for 4, if you have the stomach to do it for 4, what if I made even more? I think you're going to lose your stomach for this very quickly, and you're not going to want to do it this way. In general, if I have n, you have to apply trig identities n times. That sounds absolutely awful. So let's see if we're not going to use way 1. Maybe there's a way that way 2 can pay off. So now we're summing exponentials. And this doesn't at first really look any better, but let's do some factoring. We factor out this piece of it, right? Because that has nothing to do with n, and we park it outside. Now look at what's inside the sum. What's inside the sum is a geometric series. Maybe it doesn't look like a geometric series, but look, this is something like a to the n, the thing that changes, a to the n, a geometric series. How do you sum a geometric series? Well, you know how to do that already, and you end up with something that looks like this. Okay, this may not look much better, but we're going to do our same factoring trick that we did before, so let's park it up here. Let's now do the exact same trick we did before. In other words, I'm going to pull, last time I pulled out half of that, I'm going to pull out half again. So I pull out half again, and now I end up with something on the top and something on the bottom that look like the same thing, and the thing that they are is actually sines. So now I have the sine of n phi over 2 on the top and the sine of phi over 2 on the bottom, and a bunch of junk that depends on time. So that when I average over time, that's all going to disappear. In other words, this is crazy. I've found with complex variables the general case for n slits quite easily, and I found that somehow the intensity is proportional to sine squared of the number of slits times this phase factor that we already know, divided by just the sine squared of the phase factor. Okay, so what do I do with all this? One thing to note is that I just said it's proportional to. I kind of got sloppy with my amplitudes and stuff, but one thing to note is we know what this pattern is going to look like, because at the center, I know that they should all be in phase, because look, they all have the same, they're all offset by the same amount. In other words, the distance they travel is the same. So I'd better have a maximum there, okay? So that corresponds to phi equals 0. So if I just look at what I have and I say, all right, that's sine of 0 over sine of 0, which is undetermined. That's bad news. So let's fix this. So we have sine phi roughly equal to phi for small phi. That's a pretty easy thing to do. And then, okay, let's see what that buys us. Let's say that I say that the amplitude is equal to some value I naught when it's at the center, and there's some coefficient in front of this a, such that I need this whole thing to be equal to I naught. In other words, it has some I naught at the center, right? Okay, well, if I use my small angle approximation, then the sines turn into just the angles squared, okay? And then everything cancels except for the n squared up top. So I can actually solve, this is a funny thing to do, but I can actually solve for the amplitude. And now instead of just talking about what it's proportional to, holy smokes, I have a real honest-to-goodness formula for the intensity due to n slits, which is something that most introductory books don't do at all. Okay, let's just do a sanity check, because we did a lot of weird stuff there, and let's just see if this is consistent with what we did before. So let's find I2 using this formula. In other words, plug in n equals 2. If you plug in n equals 2, oops, I dropped my I naught. If you plug in n equals 2, you get an I naught over 4 times the sine squared of phi. And you're like, that doesn't really look like I2, but okay. You like trig identities? There's a trig identity for you. I can split the angle into 2, and then in this case, you'll see the sines kill the sines. This 2 gets squared and kills the 4, and holy smokes, this formula actually works. Okay, now, another way to look at this is, rather than saying I have n slits, I can say that my entire apparatus has a width of a, and I put n slits in it. So what does that mean? That means the distance between each of these slits, the thing I've been talking about this whole time, d, is a divided by n. And now I just want to ask you to imagine what happens if I increase the number of slits. I increase the number of slits. Well, okay, I've increased the number of slits. What happens if I do it again? I increase the number of slits. Take a look at this and compare it to what there was before. I think you'll agree that there is less material than there was before. In other words, if you have a solid piece of material and you start cutting slits in it, well, if you keep cutting slits in it, eventually you're going to run out of material. You're not going to be able to make slits anymore. In other words, if we make an infinite number of slits in this apparatus, then we'll just have one giant slit. It's kind of a weird thing to think about. But what I'm saying is, let's take the limit as n approaches infinity of the number of slits. We're going to use this formula. But instead of using d, I'm going to say take the limit as n approaches infinity. The distance between my slits is that. In other words, one slit is the case of n slits as n approaches infinity. That's pretty amazing. So this may not look particularly pleasant to evaluate, but it's actually not so bad. We're going to use our small angle approximation again. Look, if n is very large, then this angle is very small. So if we do that, we make our small angle approximation. I don't have to do anything to the top. I'll just leave the top alone. On the bottom, the sine has gone away, and look at this. N squared kills n squared. In other words, there's really no limit to evaluate once I've said that the sine is small. So I actually recover a formula for when I have an infinite number of slits. Oh my God, holy smokes. What does that mean? That means that I now have a formula for one slit. Let's just put this all together and see what this looks like. What we learned is that using the exact same technique all 3 times, Two slits looks something like this. I've made a plot of what the intensity for two slits looks like. Okay, it looks something like this. This is pretty familiar. Then we did end slits, doing the exact same technique. Admittedly, the graph here is a little weirder, and I should say that it depends. This is actually the case n equals 6. If you do different ends, it'll look different, but basically what you get is large peaks, and then little mini peaks in between. The main thing that you use end slits for, these are called diffraction gratings, is you're mainly interested in, these are called the principal peaks, And then what else did we do? We just said, look, what's a diffraction grating with an infinite number of slits? It's one slit. And so I plotted this, and what you end up with is some large central maxima, and then you end up with smaller peaks out toward the edges. Okay, so I just want to emphasize the point. Look, we did a little bit of funny complex variables. If you've never seen it before, then maybe it's weird, but look at what we accomplished using all the same technique. Okay, hopefully this video was more helpful than confusing.